in the last class, we were talking about properties of the group. In the last class, we have seen that identity element is unique. In group, we have identity element, okay, and that is unique. Also, inverse of every element is unique. Also, cancellation property we have left cancellation property, so you can cancel on left, you can cancel on right. So we have right cancellation property. Okay, and we have seen all of them. We already know that A B whole inverse, that is same as B inverse A inverse in a group. In a group, this will happen. So this we have already seen. Okay, now let's move on. Let's see this question. This is interesting question. If I give you this equation, so let's assume you have a group. Let's assume you have a group G comma star. Okay, and now if I give you this equation, AX equal to B, then what is A? Sorry, then what is X? If I give you this equation, then find X. Then find X. From this equation, AX equal to B, then find X. So how will you find? To find X, what will you do? This is very easy. To find X, what you can do, because you want X. So what you can do? You can multiply with A inverse, both sides. So you want X. So what you can do? You can multiply with A inverse. Just multiply with A inverse on both sides. Just multiply with A inverse on both sides. On both sides, you just multiply with A inverse. This is what you do. Now you can notice what this will become. This will become E. EX equal to A inverse B. And from here, I can say X is equal to A inverse B. So the value of X will be A inverse B. Is this clear? So from this equation, value of X will be A inverse B. Value of X will not be B inverse A. Value of X will be A inverse B. Okay, so this is how you can find. Is this clear to everyone? Now some interesting question. Remember this point, that value of X is not equal to B A inverse. It's not like this. This will be this A inverse B. Now one interesting question. Can I say this will be unique? Okay, so this is my question, that you have a group. I'm talking about a group because in a group you have inverse property. See, because you have a group, in group you have this inverse property. This we can use because it is a group. This A inverse is there because of group. Because we are talking about group. Because of group we have A inverse. Is this clear? So this being a group is very important. If you don't have group, then you can't say A inverse. You can't multiply with A inverse, because maybe A inverse is not there. Maybe A inverse does not exist. So because of group, you can do this. And because of group, you can avoid the parenthesis. Because of group, you can ignore the parenthesis, because group is associative. Okay, let's move on. So in a group, you have this equation, AX equal to B. We know that X will be, A inverse B. But can I say this is the unique value? But my question is, can I say this is the unique X? Can I say that X equal to A inverse B is unique solution? Is unique solution of this equation? So for this equation, can I say this is unique solution? We know this is a solution. We have seen. We know that this is a solution. We know this is a solution. Okay, X equal to A inverse B. This is a solution. But can I say this is a unique solution? This is the question. Can I say this is a unique solution? Very simple. See, whenever you want to prove something unique, then what to do? How will you prove it? What is the proof idea? What is the proof idea? Assume there are two solutions. Assume not unique. Yes. Prove by contradiction. Proof by contradiction. Proof by contradiction. Assume there are two solutions. Okay, just assume that. So prove by contradiction. Assume there are two solutions. Assume two solutions of AX equal to B. So for this equation, assume you have two solutions. And what these two solutions are? let's assume these two solutions are I can say y comma z. Let's assume you have two solutions y comma z. Just assume. Okay, very simple. Because remember, the question is asking that this is your ax equal to b. You already know that from this equation I can say x equal to a inverse b. This is a solution. So x equal to a inverse b. This is a solution. But can I say this is unique solution? How can I say that this is unique? So what I will do? I will do proof by contradiction. What I will do? I will assume that there are two solutions of this equation. Okay, now what this means? So x equal to y is solution. What this means? What this means? And what this means? X equal to z is solution. What this means? So x equal to y is solution. It means ay equal to b. And x equal to z is solution. It means az equal to b. Agree? So because these are the solution, you are saying that these are the solution. You are saying y comma z are solution. It means x equal to y is solution. It means it will satisfy. X equal to z is solution. It means it will satisfy. So what I got? I got ay equal to b, az equal to b. Now what can I say? Now this and so b, both are b. So I can say that. So I can say that ay equal to az, and you can do the left cancellation. You can do left cancellation. So y equal to z. So the two solutions are same. That's it. Yes or no? This is the proof. So basically, if you assume that there are two solutions, if you assume this, then they will be same. It means okay, the solution is unique. This is your proof. Very simple. Can you notice all the proof are like this? Nothing else is different. Every proof is like this. So far we have done almost 6 or 7 proof, I think. Maybe around 10 proof we have done so far in the group theory. Can you notice all of them are like this? The same thing we are doing. Okay. So this is the idea. So finally, this is the theory. This is the theorem, and this theorem is important. This theorem is important that in a group, if you have a group, then this equation will have unique solution. It will have unique solution. Okay, so this is the idea. So this is the note. So in group, if you have a group G comma star, okay, in group, what will happen? This equation ax equal to b has unique solution. Has unique solution. And what is that solution? What is that solution? Has unique solution x equal to a inverse b. This is the unique solution for this equation. Just multiply with a inverse on LHS. Similarly, this equation x a equal to b, this also has unique solution. What will be the value of x? Tell me, what will be the value of x? That will be b a inverse. Just multiply both the sides by a inverse. Just multiply both the sides by a inverse. Then you can see that x equal to b a inverse. Okay, so this is the idea. Unique solution. Now, one interesting consequence of this, I will tell you. What is that? One interesting consequence of this in Kelly table, application of this theorem. This theorem has very interesting application in Kelly table. In Kelly table of group theory, in Kelly table of group, what will happen? In Kelly table of group. So now notice that in Kelly table of group, is it possible, like for example, let's assume you have let's assume you have some y here, and let's assume some z you have here. Is it possible that you can have b here, you can b here? Is this possible? See, this is not possible, because remember, you already know that a variable, take variable ax equal to b, this has unique solution, right? Ax equal to b has unique solution, you already know this. Okay, because you have unique solution, so it can never happen that two different elements you can do. Is this clear? Because Ax equal to B has unique solution. So X will be, okay, there is unique X which will satisfy this. There is unique X will satisfy. There is unique X will satisfy this. Will satisfy. There is unique X will satisfy it. So this can never happen, right? Y comma Z can satisfy. Yes or no? Agree? Because unique X will satisfy. So this can never happen that Y comma Z, two things are satisfying. So this type of situation can never happen. So in Kelly table, this type of repetition can never happen. Okay. Is this clear? This type of repetition can never happen. I will come back to this point but the point is very simple. Okay. I will come back to this point again. Just wait for it. Okay. But just understand this theorem is important. Ax equal to B, this has unique solution, that will be X equal to A inverse B. And similarly, this equation has unique solution, and this is the unique solution. Okay, let's move on. I will come back to Kelly table. Don't worry. Okay, just don't worry about it. I will come back to it. Let's see this one. In a group, okay, this is my question. You tell me about this one. If you have a group, everything is happening in a group. Okay, in a group, let's assume there is A belonging to G. Okay, there is some element A belonging to G, and let's assume A square is equal to A. A square is equal to A. Then what can you say about A? Then what can you say about A? See, in a group, am I saying that for every element? Am I saying that this group is idempotent? Does it mean this group is idempotent? No, I am not saying this group is idempotent. I am saying there is some element. There is some element. Remember, I am not saying that group is idempotent. Remember, this whole thing does not mean idempotent group. This thing does not mean group is idempotent. This thing does not mean that group is idempotent, because we are making a statement for A, because we are not saying for all A. We are not saying for all A. Okay, so this we are saying for a particular element. Now what is A? This is very easy to find, because the question is saying that A square is equal to A. It means AA is equal to A. Now tell me one thing. Can I write it? AE? I can always do this, right? I can always write A as AE. This A I can always write as AE. Okay, I can always do this, correct? I can write this. Okay, so this is what I can do. For every element I can do this. Whatever element I take, I can write it as XE. Now you can see, just do the left cancellation. In a group, left cancellation you can do. So A will be equal to E. That's it. So A will be equal to E. You can, okay, you can also use this theorem also you can use. If you don't want to use this, then use this solution. Can anyone use this theorem, unique solution equation? Can anyone want to use this theorem? Alternative, so okay, proof 2 or method 2. What is the method 2? Method 2 is AA is already given to as A. Okay, so this will have unique solution. You can think this is your X. Just think this as your X. Then what can I say? This will have unique solution, and that will be A inverse, and that will be E. And this is the unique. And remember, this is unique solution. In group, I can always do this. Why? What is the reason? In group, I can always write this A is always equal to A for all A. Why? What is the reason? By the definition of identity element. By the definition of identity element, This is just the definition of identity element, nothing else. By definition of identity element. Okay. So anyway, so this proof is clear. A equal to A. So you can consider this A, you can consider as X. Then you can notice that A will be equal to A inverse. So this will be the unique solution. A will be E. Very simple. So this is the point. So this is your theorem. If, okay, for any element A, if A is square equal to A, then A will be equal to E. Now let's see this one. Which statement is correct? Is this second statement correct? A equal to A. Is this second statement correct? Yes, by definition of, yes, this is true by definition of identity element. This is true by definition of identity element. Okay. By definition of identity element, this will always happen. And what about this? If B star A is equal to E, then what is A star B? So you have a group. In this group, this is given to you that B star A, okay, this is if B star A is equal to E, then what is A star B? Then what is A star B? The question is asking this. So you have a group, then what this will be? Now you can very easily see the question is asking for A star B. If B star A is E. So tell me, if B star A is E, then what is B? From here, you can find B. You will get a unique solution. What will be B? B will be A inverse. You already know. Okay. So from this, I can say that B will be A inverse because BA equal to E. See, this is given to you. Already it is given to you that BA is equal to E. BA is equal to E. Then what can I say? I can say, I want to find B. I want to find B. Then what I can do? I can multiply like this. I can multiply like this. So from here, I will get B equal to A inverse. Or you can use the theorem because I told you that BA equal to E. So you can just assume that this is your X. So what will be B? The unique solution. The unique solution will be EA inverse, which is A inverse. And this is the unique solution. Okay, so you can use this. So very simple. So from this, I can say that B equal to A inverse. Now what is A star B? Now what that will be? Remember, B is equal to A inverse. This is your A inverse. And A inverse, that is your identity element. So A star B will be identity element. Okay. What is idea number 2? What is idea number 2 here? Here, what is idea number 2? See, look at this equation. You have a group. You have a group that is G comma star. This group you have. And this is given to you that AB is equal to E. This is given. Now tell me from here, what can you see? Tell me, what can you see? Can you notice that AB equal to E? So this B is working as what? AB is equal to E. X, Y is equal to E. So what this Y is working like? This Y is working like X inverse. This Y is working like X inverse. So this B is working as A inverse. Okay. So finally, I can say that this B is A inverse, and hence I can say that finally the question is asking what is BA? What is BA? So I can very easily do B equal to A inverse. So BA will be equal to this, and this will be equal to E. Okay. So this is your idea number 2. Just think that AB equal to E. It means this B is working as A inverse. So this is the simple idea. Okay. So this is also correct. This we have proven. So all these properties we have seen. Every property of group we have seen. Did you understand them? We know that in a group, we know that A inverse equal to A inverse A. Does it mean abelian? We also know that AE equal to EA. So do they imply abelian? Do these imply abelian? The answer is no, because these commutative property will always be there in every group. I told you in the last class. The same thing we have seen. Okay, this we have already seen. So this basically this means that do they imply abelian? These commutative property are there in every group. These commutative property. These commutative properties are in every group. Okay, let's see. So this is the final conclusion. So all these things we have seen. So in a group, these are the properties. Identity element is unique. Inverse of any element is unique. We have left cancellation law, right cancellation law. We can do left cancellation. We can do right cancellation. AB inverse is equal to B inverse A inverse. Identity element is odd on its inverse. E inverse is equal to E. What is order of a group? That is a number of elements in the group. This is the order of a group. Finite group means number of elements is finite. Okay, so all these are the properties we have already seen. Proof we have seen. So all these properties, tell me, is this property we have seen, right? If C square equal to C, then C is equal to E. We have already seen. C square equal to C. It means this C is working as E. It automatically means this C is working as E. Okay, so you can notice. So in a group, if you have a group, then these properties will be satisfied. If AB equal to AC, then you can cancel. Left cancellation law you can do. A inverse, whole inverse will be A. Okay, inverse is unique. This equation will have unique solution. This equation will have unique solution. So all these properties are very important and we have seen all of them. Did you understand all of them? Now I am going to ask you two questions. Did you understand all of them? Every proof is very easy. And let me tell you, in group theory, proof is very important. When you solve the previous year GATE exam questions, then you will be thanking me. Okay, the same type of proof you will do in all the previous year GATE exam questions. If you understand these simple things, then you will get 2 marks in the GATE exam. Definitely you will get. Okay, let's see this question. In a group, let B comma C be different elements. Is it possible that AB equal to AC? Is it possible? In a group, B comma C are different element. Is it possible that AB equal to AC? Is this possible that AB equal to AC? The answer is simply no. The answer is simply no, because B comma C are different. And you know that AB equal to AC, you already know this. See, you already know that if AB equal to AC, then what will happen? If AB equal to AC, then because it is group, so you can do left cancellation. If AB equal to AC, then B equal to C. And what is the contrapositive? What is the contrapositive? So I can say if the contrapositive, if B is not equal to C, then AB is not equal to AC. Agree? Very simple. The contrapositive. So contrapositive, you can write the contrapositive. So I can say that if B is not equal to C, then AB is not equal to AC. Very simple. Okay, remember, from this you can notice that if B comma C are different, then AB can never be same as AC. Now this is the consequence. Just again come back to Kelly table. Kelly table of group. In Kelly table of group, you can notice that if B comma C are different, then you can notice this can never be same as this, right? Yes or no? Yes or no? In Kelly table, if B comma C are different, then you can notice this can never be same as this. AB can never be same as AC, because you know this. Because if you already know, if B is not equal to C, then AB is not equal to AC. Just use this. So can you notice that in a Kelly table, you can never have repeat. In a Kelly table, you can never have repeat. You can never repeat the element in any row. In any row, you can never repeat any element. Similarly, in any column, you can never repeat any element. Okay, so this we already know. A inverse whole inverse, that is A. Just tell me this point. How will you prove this? Prove it. How are you going to prove it? In a group, can we prove that A inverse BA whole cube is equal to A inverse B cube A? How to prove it? So this is what we need to prove. Okay, this is what we need to prove, that A inverse BA whole cube, this is equal to A inverse B cube A. See, don't remember these. Okay, don't by heart this. Will you remember this? Will you remember this? No. In the GATE exam, they can ask you anything. They can ask you something else. So you have to understand. Don't remember this. Do not remember this. Just let's see how to prove it. What? Okay, see what this means. Okay, just expand this. This means A inverse BA, A inverse BA, A inverse BA. Correct? Okay. Now what this means? Now this means what? This means E. This you can remove. This you can remove. So finally, what I got? I got A inverse B, and this is E. So this will become E. So you can remove it, because identity element does not. We don't care about identity element. Identity element will not affect. So you can just remove it. Okay. So you will get B, and then you can remove this because this is identity element. So finally, what I got? I got A square B cube A. Yes or no? That's it. This is your proof. Hence proof. Very simple. Okay. Just expand this because this is the cube. So just expand. Very simple.